Okay, so we talked about last time here gases. We talked about root mean square velocity. Which is the square root of 3RT over the molar mass. And you can use this to calculate how fast, or I guess how slow a gas molecule is moving. I think we also talked about partial pressures last time as well. Remember that partial pressure basically is when we have a mixture of gases. And if we have different gases in that mixture, each gas will partially contribute to the total pressure, which is why it is referred to as partial pressures, partial pressure of A plus partial pressure of B. You add them together. Very commonly, we calculate partial pressure by just using the ideal gas law, PV equals nRT, and we use it individually for each one here. The reason we could do that is, as we talked about, it's sort of an ideal situation. And one of the things that makes something an ideal gas is the idea that there is no attractive force or repulsion force between gas molecules in an ideal situation, which means even though they are in the same sort of container, you can assume that they are almost in there by themselves. So you basically just do kind of two individual gas law, 2 or 3, depending on how many you have, gases in there, individual ideal gas laws, and you basically just add up all the pressures to give you your total pressure. Another common way that you could also do it as well is to use this equation here. And this would be a situation where you may not have enough information to go into the ideal gas law, but what you do have is an ability to get to the moles of all the gases that are there. And that will allow you to calculate the mole fraction that we talked about. And really, if you can't get to the moles and the mole fraction, and you pretty much have one of the other pieces of information, either the total pressure or a individual partial pressure, you pretty much can solve for everything else that you need. So that's sort of an alternative if you basically just have basically the moles of each of the gas and a pressure given to you. We also talked about sort of the third way of partial pressures, which is as a result of how the gas is collected. So very often, if you collect a gas over water, where basically the gas comes in, the water goes out, and you end up with this empty spot. The result of that is we will get the gas we're interested in, but we will also get some water vapor that will come along for the ride. The water vapor is not really a result of the actual chemical reaction that you're looking at. It is just a result of how you're collecting the gas. So it's sort of a byproduct that you really are not interested in. And what that basically means is the total pressure in that situation would be the pressure of the gas plus the vapor pressure of water, which is what that is. And that is a value that typically you do look up in a table based on temperature. So it really does become just really a subtraction problem where you take the total pressure minus the vapor pressure of water. And this is sometimes referred to as getting the pressure of the dry gas as you sort of subtract off water's contribution to the overall pressure. And that usually is the pressure that you want to use in any type of calculation that you may be doing. We also talked about gas effusion and diffusion, and the idea that gases will mix, based on sort of their speed, if you will. So for example, we saw a picture where I think we had some ammonia, I think we had some HCl, and they kind of mixed closer to one side versus the other. And again, that had to do with basically the speed at which those gas molecules are moving, as to which they do come together. Any questions on any of that stuff there that we talked about, I think? Okay, so to finish up talking about the gas chapter here for our examination on Tuesday, we're going to talk about what is sometimes referred to as real gases. Real gases are like real gases, unlike those fake ideal ones we've been talking about. No, I'm just kidding. So real gases are really gases under usually very large pressures and also really small, not small, but really low temperatures as well. So low temperatures, large pressures, real gases come into play, and they're really the same as other gases. But there's a couple of things that we do have to take into account, and that is the two things that make something an ideal gas, which is that the volume of the gas itself is basically negligible or zero, and that there's no interaction between the gas molecules. So under ideal conditions, pretty much we don't take those into account, but under these really large pressures, as you can see from this graph here, when we get into some pretty big pressures, the ratio of PV over RT, we start to see a lot of deviation from an ideal gas. And that means that what's coming into play is repulsive forces and attractive forces. So those two things are going to be really important in terms of the pressure that we may associate with the gas under these conditions, and also sort of the volume of the gas under these conditions as well. So let's talk a little bit about real gases here. They do not behave like ideal gas under high pressure or low temperatures. Again, when we have really high pressures, as we talked about with Boyle's law, what does that mean about the volume? The volume should be really small, right? Which means if it's a really small volume, we now have a couple of things happening, as we'll talk about. We basically have the gas molecules, which are definitely really close to one another. They're in the same spot. So there is definitely going to be interaction between them. They're going to be near each other for a much longer period of time. So we are going to get some interaction in terms of repulsion and attractive forces. The other thing that's important as well is, like I kind of drew it here, the size of the gas molecules compared to the container now is relatively important. It's not negligible, as opposed to if you had a much larger container and a smaller volume of the gas, the much larger volume in the container, we don't have to take that into account. So what we see is at low temperatures and high pressures, the 22.414 molar volume that we assume in an ideal situation does start to vary as we look at different gases. And what we see is that interaction happening that's really important, the volume interaction and that pressure interaction. So because real molecules really do take up space, as sort of my drawing there, in that really small volume, the gas molecules volume is no longer going to be considered sort of negligible compared to the space it's in. We do have to sort of take into account the actual volume of the gas in real gas situations. And that's what we see here. We see argon in sort of a real gas situation versus an ideal situation. And we see that the molar volume is starting to separate as we sort of hit these very high pressures. Before that, in sort of an ideal situation, they're pretty neck and neck, but as we grow in terms of those pressures, we really do have to sort of take those things into account. So the effect of molar volume, the higher the pressure, the amount of space occupied by the molecules, again, is going to be significant. Van der Waals, who pretty much does all the sort of intermolecular forces, and a lot of work with intermolecular forces, we'll talk about in the next chapter, which is basically the forces that hold one molecule together with another and sort of how they interact with one another. He basically modified the ideal gas law to account for the difference in the molar volume that we see in a real gas situation. And that is what is sometimes referred to as Van der Waals constant, or the B constant. There's an A constant and a B constant. Now, these constants are values that you can find in tables, and they are specific for different gases. So the Van der Waals constant for real gases are early table values. And again, if you have, say, CO2 versus O2 versus some other gas, you will find some different values for each of those individual sort of gases. So he took sort of the V part of the ideal gas law and sort of incorporated this scary looking kind of correction, but it is all the same stuff from the ideal gas law. That's obviously our moles, our gas constant, our temperature, our pressure, plus the moles. And again, this van der Waals constant specifically for whatever gas that you would look up in that table. Now, in addition to the volume, we also will start to get, as I mentioned, because because of just the sheer location of where everybody's at, we will have everybody around each other for a much longer period of time rather than a much larger volume where they're just kind of passing really quickly by each other. In this case, they have really nowhere to go. They're just going to constantly be near each other. So we do get the attractive forces and sometimes the repulsion forces that can occur at gases at really low temperatures. And that's what we see here again as we're coming down with argon. As we start dropping the temperatures, we start to see some deviation from an ideal situation. So van der Waals as well sort of did a correction factor for the attractive forces that we see in a real gas situation. And that's what's known as van der Waals constant A. And once again, it is specific for different gases. And again, this is still our ideal gas law stuff. That is our constant. And again, this is our moles and our volume squared. So why is all this important? In sort of a ideal situation, our gas molecule here would be frankly free to go bang the wall there, right? With no effect of any other gas molecules that may be near them. But if this gas molecule here in the middle does have some type of attractive forces to some other gas molecules that is there, it's going to create sort of a drag, if you will, right? As it's moving towards, say, the wall, it's now going to feel a little bit of a drag coming back the other way. And what that's going to affect is obviously the number of collisions that will occur, and that's going to obviously affect the pressure that we would associate in sort of a real gas situation versus an ideal gas situation where we assume that they're just basically flying around by themselves, nobody's interacting, so they're kind of free to kind of flow around as well. In addition, you could have some repulsion forces, which also could send the guy into the wall as well, right, as it tries to get away from other gas molecules. So you could have both of those intermolecular forces sort of happening. So what the van der Waals equation for real gases looks like is a scary version of the ideal gas law, right? And it is P plus AN squared over V squared. That is our correction for the pressure. Once again, A is found here in the table. And as you can see, there are different values depending on sort of what gas you're dealing with. And our volume is corrected as well. We're using our B constant and our nRT. You really do just solve this the same way as you would an ideal gas law. The key is, you just want to make sure if you do go to a table and find these values, sometimes the units aren't what you need. So you just got to make sure they are the right units. This would be something like the units that you would need and everything would sort of cancel out. But sometimes, depending on the table, it may not always be in maybe atmospheres or liters or something like that. So you might have to do some conversions. Now, the van der Waals equation here for real gases and real gases is really, if you think about it, versus the ideal gas law, which is PV equals nRT. The van der Waals equation really is a more specific gas law, which does depend on the gas that you're dealing with, because obviously you need to go grab the correct values off of these tables. Now, most of the time, we really don't deal with this because under normal conditions, we are in a sort of ideal situation, and we can use the ideal gas law, which really is a more universal gas law, because frankly, it doesn't matter what gas you're dealing with, you can just put the values in there for it, rather than if it's a real gas situation, you got to go find the correct ones. And if you then want to calculate it for a different gas, you got to go find those values and stuff like that. So the reason really, if we go back to sort of that very first graph that we were looking at there, is here, it that way. Now, under most conditions, right, we are hanging out in pressures right about there, right? Right, 1 atmosphere is like way over here, right? It doesn't really start deviating until you get into, the 100 atmospheres or so forth like that. And under normal conditions, even if you were a little bit higher in pressure in terms of 1 atmosphere, there's not much deviation that is happening in that little region where we normally, kind of deal with gases. And that's why we, in most cases, could just apply PV equals nRT to most situations. But if you do start to really build up some pretty big pressures, you can see some big deviations that do occur. But under most conditions, that's why we kind of go to the ideal gas law and we assume ideal conditions, because under sort of normal conditions, that's probably pretty close to what we're dealing with. Again, even if we weren't exactly at 1 atmosphere, a little bit higher, there wouldn't be that much deviation from the ideal gas law and probably the sort of real gas law that you would have. Any questions on that there? All right, that wraps up chapter 8. All right, so we're going to talk here about some intermolecular forces. We're also going to talk obviously about the liquid state, and we'll talk about some solid stuff here towards the end, I think. So first we're going to talk about intermolecular forces and intramolecular forces, and that was a good talk. Let's first start with intermolecular forces. So intermolecular forces are really those van der Waals forces, they're sometimes called. They are the forces that basically hold one entire molecule together with another. So they're the forces that basically, if you have one molecule, it is the force that basically will hold it together with another molecule. Now, this could be two of the same molecules. This also could be two different molecules and how they interact with each other. But they are basically the forces that hold one entire molecule together with another. All intermolecular forces, which we're going to talk about some different types here in just a second, all intermolecular forces basically are the same type of interaction. They are basically all, you have a positive side of one molecule is attracted to the negative side of another. So they're all basically that electrostatic attraction, opposites attract. And that's basically what every intermolecular force basically is. There are different strengths in terms of intermolecular force. Some are stronger than the other. And intermolecular forces are really responsible for important things like melting points and boiling points, for example. So, for example, if you had an intermolecular force here between, the same molecule that's holding basically this molecule together, and if this was a relatively strong intermolecular force, we would expect to see much higher boiling points and melting points. So we must just be higher melting and boiling points in a situation where we have a really strong intermolecular force. That is because it would take more or less energy to break that thing. If it was really strong. It would take more energy, which would require a higher boiling point or melting point to sort of get there, to get enough energy to allow that guy to start to sort of break apart. And that would be opposite if we have things that are held together by a really weak sort of intermolecular force. It's not going to take a lot of energy to allow that bond basically to break between them. So you just look at it wrong and it will sort of break apart. It doesn't take a lot of energy to do so. As we'll talk about, a lot of organic compounds are held together by very weak intermolecular forces, and that's why they're sometimes referred to as being volatile, which you remember from the safety video is, something that will go into the gas phase really, really easily. And then if there's fire, it explodes, right? If it's near it. Now, this is different than intramolecular forces. Intramolecular forces are the forces that basically hold one individual molecule together. So intermolecular forces holds a molecule and a molecule together. An intramolecular force is like what holds, say, if you took one water molecule, the oxygen and hydrogen bonds that are there, those are also known as covalent bonds, right? And like ionic bonds, which is electrostatic attraction. These are examples of intramolecular forces. And these intramolecular forces are always much, much stronger than any intermolecular force that you have. And the easiest example of that is taking something like water. Water, which is a polar molecule, again, has a negative side and a positive side. And when you got a couple of water molecules together, the negative side of one is attracted to the positive side of another, and that is an intermolecular force. As we'll talk about, that's what's known as hydrogen bonding. And we know that that force is much weaker than the intramolecular force that we have up here. because frankly, when we start to heat up water and we start to boil water, the bond that really breaks is the bond between the two different water molecules, allowing each of these water molecules basically to go into the gas phase, right, and create steam that you see as the thing is starting to boil. If it was opposite and the intramolecular force was much weaker, what would happen is as you start to boil or heat up water, these bonds would break. And that would be probably bad because then you'll make some hydrogen gas and oxygen gas. And I imagine if you're heating it up at that point, that probably would not be so good. So we know just from that example that obviously this does not happen, but it does break this bond here first. We also know from some conversation, I think if you heat up something that's ionic, right? You could heat it up and it will never go into the gas phase. It will just start to melt, as we talked about. Again, because ionic compounds are held together by electrostatic attraction, which is an intramolecular force, probably the strongest sort of forces you could have to hold something together. And that's why they'll never really go into the gas phase. So let's talk a little bit about some intermolecular forces. So all these forces that we're going to talk about here, these are all intermolecular forces, the ones that hold one molecule together again with another. The first type is a dipole-dipole force. And you may remember dipole as those arrows when we talked about bonding and things that have a dipole moment. Things that have a dipole moment are polar or nonpolar. They are polar molecules. So dipole-dipole interaction or dipole-dipole force is an intermolecular force that basically holds kind of one polar molecule together with another polar molecule. And again, it could be the same polar molecule or it could be two different polar molecules. What it means when something has a dipole moment is that molecule has, no matter what the situation, as you see in the picture below, a positive side and a negative side. So no matter what you do to it, it always has that unequal sharing of electrons overall, which creates a side of that molecule that will always be positive and side that will always be negative. And that works really well for what I was talking about earlier, the basic intermolecular force. When another polar molecule comes together, now the negative side of one is attracted to the positive side of another, and that is what will hold those two guys together. Now, in solid and sort of liquid, the molecules really do try to arrange themselves and align themselves to maximize this attractive force here between the positive and the negative and sort of minimize the same charges being near each other. But no matter what happens, you are going to get some negatives near negatives and some positive sides near positive sides as they all come to align. But they will continue to sort of move and kind of move around until they find sort of a livable situation where we sort of maximize those attractive forces and minimize the repulsion forces that will occur. So when we talk about intermolecular forces for polar molecules, dipole-dipole is really the main force that will hold those guys together. Questions on that there? So here's a picture again showing that the sort of maximizing the attractive forces, minimizing those repulsion forces. And again, we have that positive negative attraction happening between our molecules. Another type of intermolecular force is one that is referred to as ion dipole forces. Ion dipole forces is pretty much what the name implies. It is an ion that has a charge, and it is something that's a polar molecule that the negative side, for example, would be attracted to the positive ion. This is pretty much what happens when we dissolve something in water, some type of ionic compound in water. Like if we took sodium chloride, we know that when it goes into water, it breaks apart into a sodium ion and a chloride ion. And because water is polar, what will happen is the negative side of water will surround the positive ion, which in this case, obviously, is the oxygen side of water is more negative. And the positive side of water will actually surround the negative ion, which is the hydrogen side of water here. And this is really the process by which things dissolve. So as we know, when you dissolve something like that, that is a physical change. It doesn't disappear, doesn't go away. It is still there because we know that when we heat up something like this, a sodium chloride solution, we will evaporate off the water, and that will allow basically those ions, which are really attracted to each other, to come back together. So water here actually has a little buffer to kind of keep the ions apart. It's able to do that and sort of overcome those really strong attractive forces because there's a heck of a lot of water molecules floating around, basically in water. So there's enough of it to be able to kind of pry away those ions from each other and keep them separated from one another. So ion dipole involves an ion, either a positive cation or a negative anion, and something that is a polar molecule. And again, it's still that basic attraction between positive and negative that's happening here. Any questions on that there? Now, dispersion forces are a little bit different. Dispersion forces are pretty much what we use for nonpolar molecules. So the major intermolecular force for nonpolar molecules and how they interact with other nonpolar molecules is really dispersion forces. So if something is nonpolar, it basically will be sharing the electrons equally. And that basically means there's no like positive side or negative sides to the molecule. It's basically kind of neutral, right? Because we got nice equal sharing of electrons happening all over. So there's a couple ways the dispersion forces sort of interact. One is what is sometimes referred to as an induced dipole. And this is when we get something that does have a charge that sort of comes up to something that has no charge, like a nonpolar molecule. So for example, if we did have our kind of nonpolar molecule here, and temporarily we put like a positive charge near it, the electrons in this nonpolar molecule would be attracted to the positive charge of that ion. And what that's going to do is temporarily create a charge in that nonpolar molecule, which normally doesn't have a charge. So it's going to induce a charge here, or an induced dipole. And now that it sort of temporarily has sort of shifted its charge, it now has the ability to interact with that positive ion. Dispersion forces are pretty much temporary type of charges, temporary forces. They cannot really maintain their attractive forces over a long period of time. The reason for that is in a polar molecule, like we talked about before, no matter what you do, no matter what you back near the polar molecule, it's always going to have the same separation of charge because it's got that dipole moment. It's never going to go away and come back. It's always got a positive side and a negative side. But something that's nonpolar, the best that you could do is just sort of temporarily get it to sort of have a charge. And if that molecule or ion should kind of move away, it's going to lose its charge, and then that interaction is going to sort of break apart. That is why, if you take something like oil and vinegar salad dressing, right? You can mix it, right? And it will mix for a while, but eventually everybody separates out. And that's because the oil is the kind of nonpolar, the vinegar is kind of polar. So for a short period of time, they're able to interact using dispersion forces, but over a long period of time, they have no way to maintain that interaction. And eventually, for the most part, they will separate back out and not be able to maintain that interaction. Every molecule, even polar molecules, can do some type of dispersion forces, but it's not really their main type of interaction that they use. Again, dipole would be that. So we could have a ion-induced dipole. We also could have a dipole-induced dipole, and that's the same idea. It's just a polar molecule does the sort of inducing. So you have your nonpolar guy and a polar molecule, as a kind of my example I just mentioned, kind of comes by. Again, it's going to cause those electrons to shift like they normally would not. And again, we now get a temporary interaction between those two molecules, and they're able to basically have a interaction that will be very weak and sort of a temporary interaction with one another. Any questions on that there? Now, another way that nonpolar molecules could really interact with other nonpolar molecules is the idea that in an actual nonpolar molecule, just for any reason it wants, the electrons which are flying around, they all can decide, hey, we're gonna kind of vacation over here to the right-hand side of the molecule. And just temporarily, all the electrons can kind of end up on one side of the molecule versus the other. And that would then temporarily, once again, create a charge separation in a nonpolar molecule that normally is not there. And that's what is sometimes referred to as an instantaneous dipole. An instantaneous dipole is just, electrons kind of shifted one side to the other, creates this sort of temporary charge. And in this case, if it happened to be next to another nonpolar molecule, it would also cause those electrons to sort of shift. And now, before you know it, you have two nonpolar molecules that really didn't have any type of charge. They both now temporarily gain these charges through sort of the shifting of the electrons, and now they have a way to interact with each other. That is what is known as polarizability, the ease at which the electrons can kind of move one side or the other in terms of a molecule. It does increase with molar mass. So the strength of sort of, and this is again really still dispersion forces here, and the strength of dispersion forces will increase with molar mass. And that's because if I have a higher molar mass, I probably have more atoms. And if I have more atoms, I have more electrons. So there's a greater chance that these electrons will kind of move about. There's also greater places where these interactions could occur because it's a bigger molecule, more electrons, and more places where they actually can occur. So if you have to compare the strength of two things that both use dispersion forces, the one that has the higher molar mass should have the stronger dispersion force, even though they're both weak, will actually have the stronger dispersion force. And if you were comparing again two nonpolar molecules that use dispersion forces, the one with the larger molar mass should also have the larger boiling point and melting point because it will be relatively stronger than the guy with less electrons. Any questions on that there? Yeah, so all those that we just talked about, basically instantaneous dipole, ion induced, or dipole induced, those are all dispersion forces. And they are pretty much the weakest of all intermolecular forces that you could have. So again, that is really the major interaction that nonpolar molecules and nonpolar molecules basically use with themselves and with others. So as I mentioned before, organic compounds are typically nonpolar, especially the first several, like methane, propane, butane. Those are all what type of things in normal conditions? They are all gases, yeah? And that is because they're held together by really weak intermolecular forces. They go into the gas phase really, really easily. And a lot of other organic compounds, which are nonpolar, like I said before, are very volatile that frankly, you just like open the lid and off they go into like the gas phase and stuff like that. So because they're mainly held together by a lot of dispersion forces. All these sort of interactions in terms of intermolecular forces are also sometimes referred to as van der Waals forces that we just talked about there with the real gas law. He did a lot of work, obviously, with intermolecular forces, and he also applied that, obviously, to the ideal gas law. Now, here's a nicer picture of sort of that instantaneous dipole. Again, electrons sort of separate, causing a distribution in the other nonpolar molecule. And now we'll have a partially positive and partially negative charge, and that gives them that place to interact with one another. A special type of dipole interaction is hydrogen bonding. So this really is sort of under the dipole sort of umbrella, if you will. But hydrogen bonding is a bond between a hydrogen atom and a polar bond and an electronegative atom like nitrogen, oxygen, or fluorine. So in order to have hydrogen bonding being able to occur, you pretty much need a hydrogen that's bonded to either nitrogen, oxygen, or fluorine in the molecule that you want to do that. That is because if we look at the periodic table, nitrogen, oxygen, and fluorine, those are your big electronegativity, right? They increase in electronegativity. As we know, right, fluorine is the most electronegative. So because those are three very electronegative atoms, when they hook up with hydrogen, what they create is a nice polar bond, right? So separation of charge. And that is essential because it will create a positive and negative side to that bond where hydrogen bonding can occur. So sometimes people mistake the idea that, you know, all you need is hydrogens to do hydrogen bonding, because the name kind of sounds like that. But they do have to, it does have to be a hydrogen that's connected directly to really a nitrogen, oxygen, or fluorine to be able to participate in hydrogen bonding. That is why something like methane here, which has a lot of hydrogens, cannot do hydrogen bonding, because first off, the carbon hydrogen bond is non-polar, right? It has an electronegativity difference of 0.4, which is non-polar. So even though this guy is littered with hydrogens, it cannot participate in hydrogen bonding because there's really no separation of charge here. There's no positive side, no negative side, which is essentially what you need for that interaction to occur. By the way, this would be a non-polar molecule as well, which means CH4 would use what type of force? It would use dispersion forces, yeah. So CH4, which is non-polar, its intermolecular force would use dispersion forces. This hydrogen bonding is what we see in water. And it is why something like water has a good boiling point, and anything that has an OH bond is held together pretty strongly. It usually has a very high boiling point because, again, between one water molecule and the other, you get this bond between, say, the hydrogen and the oxygen. And in each of these cases, the hydrogen is directly bound to an oxygen, which allows you to get that polar bond that you need. And that would be obviously our hydrogen bonding. Can NH3, ammonia, hydrogen bond? It can. So that is a hydrogen that is directly attached to a nitrogen. And by the way, NH3 is a polar molecule, right? Unsymmetrical geometry. And that means in this particular case, the hydrogen more positive is the nitrogen here that is more negative, and it could hydrogen bond with another NH3 if it wanted to. And again, that way it could do that. By the way, hydrogen bonding, all these intermolecular forces are not, they are about one molecule in itself and how it interacts with itself, but it's also how other molecules, different molecules, interact with each other. That's why, for example, if you took something like this guy, which is ethanol, an organic compound, ethyl alcohol, and something like water, they can interact with each other because although this part of ethanol is non-polar, it has this polar part right here at the OH bond, which is a hydrogen attached to an oxygen, which means it can interact perfectly well with water through hydrogen bonding. And that's why certain alcohols are soluble in water, because although they contain carbons and hydrogens in the sort of non-polar part, they also contain this one little part here that is polar, and that's what gives them the ability to interact well with each other. It's an idea in terms of solubility of what's referred to, as we'll talk about, I think, in a later chapter as well, like dissolves like. So things that have the same type of intermolecular forces that they use with themselves can then interact with other molecules that use similar intermolecular forces, and that's what makes things mix together, and that's what makes things not mix together. Right? You can, yeah. Yeah, it will do a couple other things, specifically NH3, because it's actually a weak base when it goes into water. But it will actually react with water and actually will make a base in a water environment. But they will be soluble in each other in terms of this sort of interaction. They won't separate out from each other, if that's sort of your question. But in sort of the aqueous form, not the gas form, and that's how it has to interact probably with the water and the liquid water. It actually works as a base and everything mixed together. This is also why, so if you remember way back when, experiment number 3, maybe, we did the ones with the test tubes, right? With the halogens, right? And we had our different layers when we added, I think you guys use hexane. Hexane is a nonpolar organic molecule that's basically 6 carbons, and everything else is hydrogen, basically. These are all hydrogens all the way across, hydrogens and hydrogens. So that's definitely a nonpolar molecule. And that is why the bottom part, which was aqueous solution, which was basically water-based, we had that layer, sort of the aqueous water guy, where we had, like, say, sodium ions and bromide ions floating around. And up on top in the hexane layer, we had our halogens, like our Cl2, which is also nonpolar. That's how come we knew that the halogens were in the top layer, because nonpolar and nonpolar will mix well together. And on the bottom layer was our aqueous layer. And because the water layer and the nonpolar guy on top going to try to use dispersion forces on top, while the guy on the bottom was trying to use hydrogen bonding, that's again why they separated out, and you have those different layers that would occur. Any questions on that there? So to summarize the different types of intermolecular forces, on one end, we do have hydrogen bonding, which is really a dipole-dipole interaction, but it is a bond between hydrogen and nitrogen, oxygen, and fluorine. It is the strongest in terms of intermolecular forces. So if you have something that can hydrogen bond, it's going to be your strongest force. It also would relate to your highest boiling points and your highest melting points in terms of those guys. And again, obviously an example is, as we talked about, water interacting with itself, or water interacting with somebody else that could hydrogen bond. It is the strongest, it is the intermolecular force really for polar molecules that have the ability to hydrogen bond, basically. So these are really for polar molecules that have the ability to hydrogen bond. In the middle is really dipole-dipole interaction. And dipole-dipole interaction is also relatively a strong interaction. And this is really for polar molecules that lack the ability to hydrogen bond. So these would be polar molecules that lack the ability to hydrogen bond. So for example, I'll just randomly draw something here. Say we had something like this. I won't draw all the electrons. But this guy here would be this guy here would be a polar molecule, right? It is symmetrical geometry, but we don't have everything the same attached. The fluorine being more electronegative. That would create near the fluorine side of the molecule, it being more negative on this side, near the carbon hydrogen, which is nonpolar, more positive on that side. And this guy would use something like dipole-dipole interaction. He does have a hydrogen, but that is a hydrogen that cannot hydrogen bond because it's attached to a carbon and it's nonpolar. So he would only be able to use dipole-dipole interaction, and that would be his sort of main intermolecular force that would happen. Now, on the last side there, or the end side, and the weakest side is really our dispersion forces, and our dispersion forces are really the weakest. And those, as I mentioned before, are really the main route for nonpolar molecules. How nonpolar molecules interact with itself and how nonpolar molecules interact with other nonpolar molecules is through dispersion forces. Because they are, as we talked about, really temporary, weak interactions, they're dependent on electrons moving and staying, and as they break apart, new ones form, and those break apart, new ones form, and those break apart. So because they're not fixed in terms of their charge, they are temporary and weak, and those are pretty much where you're going to find your lowest in terms of boiling points and melting points in comparison, obviously, to something that could hydrogen bond. Any questions on any of those things there? Yeah. They typically cannot hydrogen bond because they don't have the they don't have a hydrogen that can participate in hydrogen bonding. Could that guy interact with maybe something like OH that does have a positive? It could, but it wouldn't necessarily be considered hydrogen bonding because you don't have sort of the right interaction. It would be more dipole-dipole interaction that would happen. So specifically, you got to kind of have these bonds kind of on both people, if you will. So like the example with the ethanol and like the water, they both have that OH sort of bond, and that's what creates that really strong attractive force between those two, because they're pretty much a pretty polar bond between those guys in terms of the difference in electronegativity. So it creates a really strong attraction between those. Other questions? Yeah. And obviously any type of non-polar guy obviously would be an example of this. So whatever C2H6, whatever you like, would be an example. Now, as I mentioned before, everybody does technically have the ability to do some type of dispersion forces, even polar molecules, which is why we get those interactions that they kind of mix for a bit, but they again cannot maintain that. But if you are asked sort of a question of, what is the sort of strongest intermolecular force, you really want to put dispersion forces for everybody. You would probably just save those for non-polar, and polar would either be hydrogen bonding or dipole-dipole interaction. But they all can technically do dispersion forces, which is why they're able to sort of interact, with each other for a short period of time. Any questions on intermolecular forces? Okay, then let's talk a little bit about the liquid state. Obviously, in the liquid state, things are still, molecules and stuff are still relatively close to one another, but they do have enough energy to sort of pass each other, right? And that's why liquids are fluid, right? They pour and make messes and all that good stuff. They do remain in motion. They're hard to compress. Viscosity is the resistance of a liquid to flow. It is related to intermolecular forces. So water has a low viscosity, motor oil has a high viscosity, and viscosity does decrease as temperature increases. As you put more temperature in there, right, you put in more energy, and that gives everybody a little bit more movement, and it's able to sort of pass each other a little bit more and would flow a little bit better as well. Let's talk a little bit about some important forces that we do see in something like water. So the first type of force is a cohesive force, and cohesive forces are the forces of attraction between molecules of a single substance. So how one molecule interacts with another. Excuse me. Something like water here, and how it interacts with another water. This would be our hydrogen bonding, and that would be our cohesive forces. Adhesive forces are how different molecules interact with one another. So the attractive forces between two different things. As we will see shortly, but we'll preview it here, this is why we get the curvature of the liquid. And we make a meniscus when we put water or some type of liquid in a glass container. And that is because the attractive forces between, say, water and the glass is actually stronger than the attractive forces between water and itself. And that's what happens is you actually see the water on the sides ride up the sides of the glass container because the attractive forces are much stronger. And that's what gives us our curvature that we see with our meniscus. That is also why in most cases we read from the bottom of the meniscus, because if that attractive force wasn't there, these guys would come back down basically to that level. And that's really where the liquid actually is. It's just sort of artificially coming up the sides because of that attractive forces that occurs. And that is because the adhesive forces here are actually greater than the cohesive forces. So we get that curvature, that meniscus that basically occurs in this case. Surface tension is the elasticity that's found on the surface of a liquid. Energy is needed to expand the surface. So for example, there's that surface tension that you can break or be very careful not to break. I guess you could lay a paper clip on there and maybe not break it. But what's really causing that surface tension, as we'll see sort of in the picture, is when we cook up the water, say molecules, for example, at the surface of a liquid versus say a water molecule that is below the surface. Sort of the water molecule below the surface is going to feel attractive forces basically all around it. So it's going to be sort of, equally sort of attracted, if you will, all around. But on the top there at the surface, there is no obviously liquid water above it. So there is no attractive forces above. So those guys really only feel attractive forces to the left, and then for those guys underneath it. So what that ends up doing is stretching the surface, right, and pulling it down, and it creates that really tight sort of surface tension that you have at the surface of a liquid because of those intermolecular forces as it pulls kind of right and left and down on it. It doesn't have that sort of balancing one that would be pulling up because obviously there's nothing above it to do that. And that's what we see here. Again, our water molecules here at the surface, feeling that attractive forces kind of to the right and the left. That's going to expand that surface there and create a really nice surface tension that you have here, as opposed to our guy sort of in the center that feels that attractive force all around it. Now, that's also why we can sometimes break that surface tension, and we can use something like soap to do that. For example, if you add soap or detergent, the surface tension in water is greatly reduced. By the way, soap is pretty much two things. It's a really long chain of carbons and hydrogens, represented by my zigzag line here. And then at the end, it has this group here, which is really a carboxylic acid type group. And this part of the molecule is polar. And again, this is line structure in organic chemistry. Everywhere there's a point, it's a carbon. And these carbons have hydrogens attached to them. This part of it, which is all carbons and hydrogens, is nonpolar. And by the way, that's how soap works, because dirt is typically nonpolar. And the nonpolar part of soap basically aligns itself around the dirt. So that zigzag carbon part traps the dirt because they're attracted to each other. That allows the polar side here of water, of soap, basically to be on the outside. This creates what is sometimes referred to as a micelle that traps the dirt inside of it, because typically after you use soap, you wash it off with water, which is attracted to the polar side of soap. And it has the dirt trapped in there. So as the water and the soap mixes, out goes the dirt that's sort of trapped in the middle of the long non-polar chain that's on soap. It's a good lesson to learn how soap works, I suppose. So it's good. But what that also does, as you might remember or you might know, if you wash your car or your car gets water or an umbrella, especially if your car has wax on it, for example, right? Wax is non-polar, right? Water will typically start to just bead, right? Rather than spread out, right? And when you go wash your car, you put your water on to begin with. And again, if it has some type of wax on it, most of it does, or even if it hasn't been waxed for a while, it still will do it in most cases. You could take the hose off the car, right? And you just have a bunch of water beads all over it, right? Then you come by with your soap and water, right? And then as you do in your soap and water, everything starts to spread out. And that's because when you do that, this polar part of soap is able to basically insert itself in between the water molecules. And what that does is sort of break the surface tension and allows the water molecules basically to spread out. Also allows your car to get washed a little bit better, I imagine, as well. And now the same thing will sort of happen as my example here, as you're washing, right, with your soapy water, right? The non-polar parts grabbing up all the dirt, right? And then you wash it off, obviously, with some more water when you're all done. Your car is clean and your dirt's gone and it's trapped in your soap. So you could break the surface tension. It'll allow everything to sort of spread out. They used to have a commercial about like dish soap that they would do like one little drop of the dish soap and you see all the dirt and stuff whoosh, like spread out. It was like Dawn or something like that. But it's the same idea, basically. It will break that surface tension, allow really everything to spread out. Any questions on that there? So as I mentioned, that adhesive and cohesive forces is really what is responsible for those meniscus that we see. When a glass tube with a small diameter is put into water, the water will rise due to capillary action. Capillary action, right, is basically it's just going to be attracted to the tube. So it'll draw the water up. Maybe you've used it maybe in some experiment somewhere. It's kind of like a closed side and an open side, really small, sometimes little tube. And you basically could just put it over there and that capillary action will allow basically the liquid to come up into the tube because of that. And that's again because of the attractive forces between, say, the water there and the actual glass to do that. As we talked about before, that is why we have our meniscus that occurs. And in this case, our badly drawn straight line there from the bottom, where our adhesive forces, the force between the water and the glass is much stronger than that between the water and itself. So we get that rise. Not all substances that is the case. Mercury is an example where it is actually opposite of that. The attractive forces between mercury and itself is actually stronger than that in the glass tube. So you actually get the meniscus upside down in the case of mercury, and you would actually read it from the top of the meniscus in this case. And that's because it is artificially dropping because of that attraction. The real sort of volume would be back up at the top of the meniscus in this case. So mercury is a prime example where if you ever see mercury, probably not in schools because they've taken them all out, but old barometers used to be mercury barometers, and you can actually see the meniscus kind of going in the opposite direction, because in this case, the cohesive forces are stronger than the adhesive forces. So the forces within the molecule to itself is going to be stronger than between that and the glass. So let's talk a little bit about vapor pressure. Vapor pressure, and as I mentioned earlier, the tendency of a liquid to vaporize is what's known as volatility. And if something is very volatile, it means it really can go into the gas phase really easily. That's why if you ever take organic chemistry, they stick you in a fume hood because most of the stuff that you use in there is pretty volatile. Plus, you don't want to smell most of it because you could smell it because it goes into the gas phase really easily. So it does increase with temperature. So obviously increasing temperature will increase the energy and allow things to sort of go into that gas phase. Liquid in an open container will evaporate completely as air diffuses away most of the gases that are entering. At the surface of any liquid, you basically have two things happening. You have evaporation, and the opposite of evaporation is condensation happening, right? So at the surface of any liquid, you basically have these guys jumping out of the liquid phase into the gas phase. And you got some slow moving guys that are too tired and they drop back into the liquid phase. So you have this constant sort of interchange that occurs. That's why when you have a little bit of liquid that's spread out, say on the bench, it will eventually evaporate, because what happens, right, is you get that rate of evaporation that's occurring all over the place, actually. And you have air that's coming in here and kind of pushing those guys away, so they're not available to come back into the liquid phase. And eventually all you got is really the rate of evaporation occurring, and eventually your little puddle there goes away. Depending on how big your little puddle is, might take a little while to do that. That's also why then if you, speaking of that, took your liquid there and say put it into a container and it was open, it would still eventually evaporate, but it would take a much longer period to do that, right? Because all these guys got to work up this way and you got a lot more volume, right? So not as much surface area, if you will, being exposed to air all at once. So it takes a much longer time for it to evaporate down. Good. It would take longer. I mean, there's even though we don't feel wind, you don't need like a strong hurricane happening to do this, right? There's just natural, obviously, flow of the air in the room, right? If you took that out, it ideally would kind of maintain if you were in a vacuum, I suppose. But when we do talk about vapor pressure, what it really is above the surface of the liquid, as that evaporation occurs, we get gas molecules, right? So we get everybody in the gas phase. That's above the surface of the liquid. And obviously things in the gas phase will cause pressure, and that is what the vapor pressure is. It's basically the pressure of those guys that basically jumped into the gas phase above the liquid surface that is there. Liquids with very high vapor pressure will be said to be volatile. They'll evaporate really rapidly. And that is because in order to have a high vapor pressure, you would need a lot of gas molecules or not so much gas molecules. You would need a lot of gas molecules to cause a lot of pressure usually. So that means in order to get a lot of gas molecules, this guy is starting to evaporate really easily, right? To allow those guys to kind of come into the gas phase. Things with low vapor pressure means you're not going to get as much evaporation occurrence because you don't have as much vapor over or gas over the liquid part of it. The vapor pressure of a liquid at a given temperature does determine the intermolecular forces that act on it. Things with large intermolecular forces tend to have low vapor pressures. Why do things with large intermolecular forces have low vapor pressures? I'll reword that. Why do things with strong intermolecular forces have low vapor pressures? They're held together, right? So it takes a lot to get them to go to the gas phase, right? So because they're held together really tightly, it's going to take a little bit more effort to get those guys in the gas phase. So under normal conditions, you're not going to get a lot of it just quickly going into the gas phase. And you would then have not as much gas over the liquid part, and you would have a lower vapor pressure, as opposed to like those organic guys we were talking about, held together by those weak dispersion forces, which means, you know, you just kind of look at them wrong. They're able to kind of get away from each other. And that's going to create a lot of gas, obviously, over, say, a liquid part. And it would be much more volatile in that case and have a higher vapor pressure. Now let's talk a little bit about liquids in a container. When you have a liquid in a container, a couple of things happen. Obviously, if we cap that thing up, that obviously is going to prevent our gas molecules from escaping, right? So that is going to obviously cut down on the total evaporation of that liquid. But what happens though, when you put a liquid in the container to begin with and you cap it up, you really do at the very beginning have a much higher rate of evaporation. At this point though, these guys have really nowhere to go, which means you're then going to get some guys decide to drop back the other way, and the rate of condensation is going to occur. What will happen is the rate of evaporation will eventually equal the rate of condensation, and it will reach what is referred to as equilibrium. And what will usually happen if you really look at it, sometimes it's easier to see than others, is you'll sometimes see a drop in the actual liquid volume from where it started. And that's because before it started, everybody was in the liquid phase, but now you have some of these guys go into the gas phase and come back down. So as they reach equilibrium, you'll typically see sort of a drop in the overall volume that was in that container. Any questions on that there? Yeah, as long as you keep the lid on, pretty much you'll be able to maintain it. And that's basically what equilibrium means. It basically just talks about, it doesn't mean that you have equal amounts, say, on both sides of whatever's happening, but really what equilibrium means, it actually has to do with rate and how fast. So as fast as it goes sort of in one direction, it will equally go back in the other direction just as fast. And what that does in a lot of cases, it doesn't give you equal amounts on both sides, but what it does, if it's going back and forth at the same rate, whenever it reaches equilibrium, everybody sort of locks themselves into where they're at. Because just as fast as you lose a little, it comes back, you lose a little, it comes back. So wherever they lock themselves in terms of, if it's molarity or pressure, or in this case, volume, the volume will be able to maintain because they're just kind of switching places basically at that point when they reach equilibrium. You'll get kind of no net gain going in either direction. And that's sort of what equilibrium sort of refers to. So there is a way to calculate the vapor pressure of a system. So this is the Clausen-Clapeyron equation. I like it. That is the natural log, and this is the vapor pressure at one temperature over the vapor pressure at another temperature equals delta H of vaporization. The delta H of vaporization is really the energy that's required to do the phase transition. So although we don't talk about delta H in this class, as we go from liquid to gas and gas back to liquid, that occurs, by the way, at the same temperature. It doesn't occur at different temperatures as you go from liquid to gas or gas back to liquid. Boiling point and condensation occurs basically, evaporation and condensation occurs at the exact same temperature. That is normally the normal boiling point of a substance where this occurs. For example, water is 100 degrees Celsius is where that occurs for water, which is a normal boiling point. R is the gas constant, but it is not the one that we use for the gas laws. It is the one that we use for the velocity. It is the one that has energy in it, the 8.314 joules per Kelvin per mole. And these are our temperatures, which, as you probably can imagine, much like anything else, does need to be converted to Kelvin here. There is some unit consideration that you need to watch out for if you happen to use this equation, and that is because delta H's are typically given to you in kilojoules, and the gas constants in joules. So you have a 1,000-fold difference between them. So you either need to convert your delta H into joules or convert your R into kilojoules. That way you will not be off by that factor of 1,000. That's a very common mistake that people make. They kind of leave one in kilojoules and one in joules, and they're just off by that factor. So, well, there's the answer right there. So we'll take a look and see how we get there. So we're going to do the vapor pressure here. So we have our natural log of P1, P2 is our delta H over R, 1 over T2 minus 1 over T1 in this case. So in this case, if we were going to solve this problem, the vapor pressure of water at 25 degrees Celsius is 23.8 torr. Which we would need to convert into Kelvin. So that's a plus 273 there, gives us a 298 Kelvin. The heat of vaporization is 43.9. The heat of vaporization is a fancy way of saying delta H of vaporization. So that is what the delta H is. Calculate the vapor pressure at 65 degrees. So we'll do a 65 plus a 273 is a 338 there. I think we're good. So it really doesn't matter as long as you keep obviously the pressure and temperature sort of together that go together. We will do the natural log here of, we'll do P1 as 23.8 torr. P2 we'll look for equals our delta H. And what I'm going to do is actually do 43.9 times 1,000. And that's going to convert that into joules, basically. So it's going to be the same units as the one below. And we're going to divide it by our 8.314 joules per Kelvin per mole. And we're going to do 1 over our second temperature, which was 338, minus 1 over our initial temperature, which was a 298 here. So I think we could kind of clean up this side. So if we clean up that side there, we could get 1 divided by 338 minus 1 divided by 298. We're going to times it by 43.9 times 1,000. And divide it by 8.314. That's going to give me something. So that's 2, I think. You can give me the natural log of 23.8 divided by P2 is equal to minus 2.0969, I believe. To get rid of the natural log, you need to take the E of both sides. Yeah, so you're going to E those guys. on your calculator. That's the little symbol above the natural log button on your calculator. Yeah. When you do this, the natural log and the e just go away, basically, right? And you end up with 23.8 over P2. And 0.12283. We're going to multiply P2 to the other side. Gives us 23.8 is equal to 0.12283 P2. We're then going to divide this back to the other side. And hopefully it is the number that's on the screen. There it is, $1.94. There it is. First P2 equals 194 torr in this case. As you can see, you don't need to convert the the pressure into atmospheres, but you do obviously need to make sure they're the same units if they happen to be different units in this case. Better? Any questions on that one? That looks like my shot. I like it. Shot of something. There it is. Any question on that calculation there? All right, we will lay it up there, I think, for today so we could get to our lab.